Right now, as you're watching this video, you think you're sitting still. But according to Einstein, you're actually accelerating upward at 9.8 meters per second squared. The floor beneath you is pushing you up with tremendous force and gravity. Well, gravity doesn't even exist, at least not in the way Newton told us it does. And here's the wild part. Einstein was absolutely right. The force you felt your entire life, the thing keeping your feet on the ground, pulling objects down, making the universe work the way it does, it's not a force at all. It's something far stranger, and by the end of this video, you're going to see the world completely differently. I'm going to prove to you that what you call gravity is actually the geometry of space-time itself, bending and warping under mass and energy. But before we get there, we need to talk about why Newton was wrong, why Einstein had to rethink everything, and what's really happening when you drop your phone and it falls to the ground. If you're ready to have your mind completely rewired about one of the most fundamental aspects of reality, hit that subscribe button right now. Because Physics Decoded is about to take you on a journey through the most bizarre physics discovery of the last century. Let's start with what you think you know. You drop an apple, it falls down. Newton said that's because Earth's mass creates a gravitational force that pulls the apple toward it. Simple, right? The bigger the mass, the stronger the pull. This idea worked incredibly well for over 200 years. We used Newtonian gravity to predict planetary motion, to understand tides, to calculate orbits. It seemed perfect. Except it wasn't. There were tiny problems, little cracks in the theory that nobody could explain. The orbit of Mercury, the planet closest to the Sun, was doing something weird. It was precessing, meaning its elliptical orbit was slowly rotating over time. Astronomers noticed this back in the 1800s, and they tried everything to explain it using Newton's laws. They looked for hidden planets, they adjusted their calculations, they checked and rechecked their observations. Nothing worked. The math just didn't add up. Mercury's orbit was off by 43 arcseconds per century. That might sound tiny, but in physics, when your predictions don't match reality, even by a tiny amount, it means something fundamental is wrong. Then there was the problem of light. If gravity is a force that pulls on mass, what does it do to light? Light has no mass, so according to Newton, gravity shouldn't affect it at all. But some scientists suspected that massive objects might bend light somehow. The problem was, nobody could explain how or why. And more fundamentally, nobody could explain what gravity actually was. Newton himself admitted this. He could describe how gravity behaved mathematically, but he had no idea what caused it or how it worked across empty space. How does the sun reach across 93 million miles of vacuum and pull on Earth? What's the mechanism? Newton called it action at a distance, and essentially said, I don't know how it works, but here's the math that describes it. Enter Albert Einstein in the early 1900s. He wasn't trying to fix gravity at first. He was thinking about something completely different, the speed of light. Einstein realized that the speed of light is constant for all observers, no matter how fast they're moving. This led him to special relativity in 1905, which completely changed our understanding of space and time. But special relativity only worked for objects moving at constant speeds. What about acceleration? What about gravity? Einstein spent the next 10 years wrestling with these questions, and in 1915, he published General Relativity. This wasn't just a small adjustment to Newton's theory. It was a complete revolution in how we think about gravity, space, and time. Einstein's big insight came from what he called the happiest thought of his life. He imagined a person falling off a roof. While falling, that person wouldn't feel their own weight. They'd be weightless, just like astronauts in orbit. Inside the reference frame of the falling person, there's no gravity. Einstein realized that this meant something profound. Gravity and acceleration are the same thing. This is called the equivalence principle, and it's the foundation of everything that follows. Imagine you're in an elevator in deep space with no windows. If the elevator accelerates upward at exactly 9.8 meters per second squared, you'd feel a force pushing you toward the floor. You'd feel weight. Now imagine you're in an identical elevator, sitting still on Earth. You'd feel exactly the same force. Einstein said there's no experiment you can do inside that elevator to tell the difference between these two situations. Acceleration and gravity are equivalent. But here's where it gets really strange. If you're standing on Earth's surface right now, Einstein says you're not stationary. The ground beneath you is accelerating you upward. Wait, what? How can you be accelerating upward when you're just sitting still? This is where we need to talk about spacetime. Newton thought of space and time as separate things. Space was the stage where physics happened, and time ticked along independently. Einstein showed that space and time are connected into a single four-dimensional fabric called spacetime, and this fabric can bend and curve. Mass and energy cause spacetime to curve. The more massive something is, the more it curves spacetime around it. Earth's mass creates a curvature in spacetime, like a bowling ball placed on a stretched rubber sheet. Now here's the crucial part. Objects moving through spacetime naturally follow the straightest possible paths, called geodesics. But when spacetime is curved, these geodesics are curved too. An object in freefall, like that person Einstein imagined falling off the roof, is actually following a straight path through curved spacetime. They're not being pulled by any force. They're just moving naturally through the geometry of spacetime itself. So when you're standing on Earth's surface, you're trying to follow your natural geodesic through curved space, which would be to fall toward Earth's center, but the ground gets in the way. The ground physically prevents you from following your natural path. The electromagnetic forces in the ground push back against you, and that's what you feel as weight. You're being accelerated upward by the ground, away from your natural geodesic. That feeling you call gravity, that pull toward Earth, is actually you being pushed up and prevented from following your natural path through curved spacetime. This is why Einstein said gravity isn't a force, it's geometry. When you drop an apple, it's not being pulled down by some mysterious force. It's following the curvature of spacetime created by Earth's mass. The apple is moving along a geodesic, the straightest possible path through curved spacetime, and that path happens to intersect with Earth's surface. From your perspective standing on the ground, the apple appears to accelerate downward. But from the apple's perspective in its own reference frame, it's in free fall and feels no force at all. It's weightless, just moving naturally through space. Now you might be thinking, okay, this is a nice philosophical way to think about gravity, but does it actually change anything? Does it matter whether we call gravity a force or curved spacetime? The answer is absolutely yes. General relativity makes predictions that are completely different from Newton's theory, and we can test them. Remember Mercury's orbit that didn't quite fit Newton's equations? General relativity predicted the exact precession of Mercury's orbit, down to those 43 arc-seconds per century. It explained what Newton's theory couldn't. Then there's gravitational lensing. Einstein predicted that light, traveling through curved spacetime, would follow curved paths. Even though light has no mass, it still has to travel through spacetime, and spacetime is curved by massive objects. This means a massive object like the Sun should bend the path of light passing near it. In 1919, during a solar eclipse, astronomers led by Arthur Eddington measured the positions of stars visible near the Sun's edge. The stars appeared shifted from their normal positions by exactly the amount Einstein predicted. Light from those stars had been bent by the Sun's curved spacetime. This observation made Einstein world famous overnight. But gravitational lensing isn't just a historical curiosity. We use it all the time in modern astronomy, when light from distant galaxies passes by massive galaxy clusters. The spacetime curvature creates multiple distorted images of those background galaxies. We can use these distortions to map out the distribution of mass in the universe, including dark matter that we can't see directly. Entire fields of cosmology depend on gravitational lensing effects that only make sense in Einstein's framework. General relativity also predicted something even more bizarre: gravitational time dilation. Time runs at different rates depending on how curved spacetime is. The stronger the gravitational field, or the more curved spacetime is, the slower time passes. Put a clock near a massive object, and it will tick slower than an identical clock farther away. This isn't a malfunction of the clock. Time itself is literally passing more slowly. Astronauts on the International Space Station age slightly faster than people on Earth. Surface because they in a weaker gravitational field where spacetime is less curved. And here's something that affects you every single day: GPS satellites. These satellites orbit about 12,000 miles above Earth's surface. Because they're farther from Earth's mass, spacetime is less curved where they are, and time runs faster for them compared to clocks on Earth's surface. The difference is only about 38 microseconds per day, but GPS works by timing radio signals traveling at the speed of light. If we didn't account for general relativity's time dilation effect, GPS coordinates would drift by about 6 miles per day. Your phone's navigation would be completely useless. Every time you use GPS, you're relying on Einstein's theory that gravity is curved spacetime, not a Newtonian force. Now let's talk about one of the most extreme predictions of general relativity: black holes. If you keep adding mass to a region of space, you curve spacetime more and more. Eventually, you can curve it so extremely that not even light can escape. The escape velocity exceeds the speed of light. This creates what we call an event horizon, the point of no return around a black hole. Once anything crosses the event horizon, it can never come back out. It's not that some incredibly strong force is pulling things in. It's that space-time itself is so warped that all possible futures point inward, toward the singularity. For decades, black holes were just theoretical predictions. But in 2019, the Event Horizon Telescope captured the first direct image of a black hole shadow. We've now imaged multiple supermassive black holes, including the one at the center of our own Milky Way galaxy. These aren't Newtonian objects that just happen to have really strong gravity. They're regions where space-time curvature becomes so extreme that the geometry itself traps everything inside. You can't understand black holes at all without general relativity. General relativity also predicts gravitational waves, ripples in space-time itself, traveling at the speed of light. When massive objects accelerate, especially in extreme situations like two black holes spiraling into each other, they create waves in the fabric of space-time that propagate outward. In 2015, the LIGO detectors made the first direct observation of gravitational waves from two merging black holes over 1 billion light-years away. Since then, we've detected dozens of these events. Gravitational waves are literal vibrations in space-time geometry, something that makes no sense at all in Newton's framework, where gravity is just a force. So at this point, you might be convinced that Einstein's geometric view of gravity is correct. But here's where things get really interesting. Is general relativity the final answer? Almost certainly not. We know general relativity is incomplete because it breaks down at the singularity inside black holes and at the Big Bang, when space-time curvature becomes infinite. The math gives nonsensical answers. We need a theory of quantum gravity that combines general relativity with quantum mechanics, and we don't have that yet. Some physicists think that at the quantum level, maybe gravity's a force after all, transmitted by hypothetical particles called gravitons. Others think space-time itself might emerge from something more fundamental. That geometry and curvature are just effective descriptions of some deeper quantum reality. String theory, loop quantum gravity, and other approaches are trying to figure this out. But we don't have experimental evidence yet to guide us. There's also the mystery of dark energy. Observations show that the expansion of the universe is accelerating. Something is causing space-time itself to expand faster and faster. We call this dark energy, but we have no idea what it actually is. It might be a property of space-time itself, what Einstein called the cosmological constant, or it might be something else entirely. General relativity can accommodate dark energy mathematically, but it doesn't explain what it is, or why it has the value it does. And then there's dark matter. Galaxies rotate in ways that suggest there's much more mass present than we can see. Either there's a huge amount of invisible matter made of particles we haven't detected yet, or our understanding of gravity needs modification. Some physicists have proposed modified theories of gravity, like MOND, that change Einstein's equations on large scales. But so far, the evidence strongly favors dark matter existing, rather than general relativity being wrong. So where does this leave us? Is gravity a force or is it curved space-time? The answer depends on what scale you're looking at and how precise you need to be. For everyday situations, Newton's idea of gravity as a force works perfectly fine. If you're calculating the trajectory of a baseball or designing a building, Newtonian gravity gives you the right answer. But at a deeper level, when you need precision, when you're dealing with strong gravitational fields, when you're trying to understand the fundamental nature of reality, Einstein's geometric view is correct. Gravity isn't a force pulling you down. It's the curvature of space-time itself. The ground beneath you right now is accelerating you upward through curved space. You feel weight because electromagnetic forces in the ground prevent you from following your natural geodesic path. When you jump, you briefly enter freefall and follow that geodesic, feeling weightless for a moment until the ground catches you again and resumes accelerating you upward. This isn't just philosophy or mathematical abstraction. It's the real physical description of what's happening to you right now. And this has profound implications for how we understand the universe. Spacetime is a dynamic, flexible thing that responds to matter and energy. The universe isn't happening in space and time as separate background stages. The universe is spacetime, and matter tells spacetime how to curve, while spacetime tells matter how to move. Everything from the orbit of planets to the expansion of the universe itself emerges from this geometric dance. The next time someone tells you that gravity pulls you toward Earth, you can tell them the truth. There is no pull. There is no force of gravity. There is only the curvature of spacetime and your own inertia carrying you along, geodesics through that curved geometry. Earth's mass warps spacetime. You follow the curves, and the ground pushes back to stop you. That's gravity. That's what Einstein revealed to us over a century ago, and it remains one of the most beautiful and strange insights in all of physics. So now I want to hear from you. Drop a comment below and tell me, does it change how you feel knowing you're being accelerated upward right now? Does the idea that gravity is geometry rather than a force make you see the world differently? And here's a question for the real physics enthusiasts. If gravity isn't a force, why do we still include it as one of the 4 fundamental forces? Let's get a discussion going in the comments. If this video bent your mind the way mass bends spacetime, do me a favor and share it with someone who still thinks gravity is simple. Send it to that friend who thinks they understand physics. Post it in your group chat. Let's spread some mind-bending physics to more people. And if you haven't already, subscribe to Physics Decoded, because we're just getting started. We've got videos coming on quantum mechanics, the nature of time, what happens inside black holes, and so much more. Hit that notification bell so you don't miss when we decode the next piece of reality. Remember, the universe is stranger than you think. Thanks for watching, and I'll see you in the next video, where we'll continue decoding physics together.